This is our second video on circular motion. So we're going to begin here to look at a particle moving in a circle. However, again, it's a bit of a tricky issue as we get into circular motion. The first kind of motion we're going to look at is linear speed. Even when an object is moving around in a circle, it can still be said to have linear speed, as if it were released, it would move in a straight line. So as this object moves around in the circle, it's moving around the circle, as it's let go, it would take a straight path. I was trying to find a decent video to show this. I looked up a few children falling off merry-go-rounds and things like that, but none of them were in decent resolution or detailed enough to use. Another example would be a cowboy lassoing a bull. The lasso goes round and round the cowboy's head, but as they let go, it takes a straight path. This might be a bit deceptive, as if you were going through the air. So for example, if you were in a circular motion and came off a swing, you wouldn't necessarily move in a straight line because gravity would kick in. But something that is released from a circular orbit or circular motion, if it is released, it will move in a straight line. So the straight line it will move in would give it a linear speed. The line is also a tangent to the circle, as it would only touch it in one place. Normally in maths, when you draw a tangent, you extend it outwards, but we only draw it one-sided, so to speak, because the object will be here and then released, so that will be the path the object would take, which would be in a straight line. So the speed can also be called the tangential speed, because it is the speed that will be shown by the tangent. Then we take another look, and we can, like always with motion, we can apply Dad-Silly triangle. So despite the circular motion, we can still apply Dad-Silly triangle, DST, with some amendments. And again, it's a bit tricky in physics because distance is often displacement, which is given the letter S. Speed is often called velocity, which is given the letter V, but time is still time. So the speed or velocity is found as above. You would take the linear speed or the tangential speed as it's released in a circle. The time is calculated as normal, and the distance is the arc length. So here the object starts here at time 1, it moves along here at time 2. So this black line here will be your arc length, which is given S, and that will be your distance traveled. Again, it's not displacement, it will be the distance traveled along the circular path. So if the object at time 1, we have the object at time 2, we have our arc length S, which is our distance traveled. So from here, well, using our velocity above, we would have our three different calculations. If we knew S and we knew T, we could then calculate the velocity or the speed as S over T, the distance traveled over the time. It's not displacement, but it is the distance traveled. It's the distance that's gone from time 1 to time 2. So we have distance, which is given the letter S, velocity, which is the letter V, and time, which is T. So even though the object is moving in a circle, it may travel at a constant speed. So in our problem here, we would assume that it's traveling at constant speed. So it is, however, even though it's at the constant speed, it is said to be accelerating as it's continually changing in direction. So that change of direction without a change of speed still counts as acceleration. And this is an important point, and it's something we will consider again later on. So even though an object moving in a circle may travel at constant speed, it is still said to be accelerating as it is continually changing direction. So we're going to take a look here at the next section. So here we're going to talk about angular velocity. So if we can imagine this arm here, this green line A, that is moving up and it's rotating around. So it goes from A up to B in a certain time. The center will be here, so it's a sector of a circle or an arc of a circle, but it could be spinning around, again moving at a regular speed. So it's moving in a circle. So the object you would think would be moving in a set speed or velocity because it's going around the same all the time. So the arm is moving at a particular speed. However, when you examine it more closely, each part of it, A, B, C, and D, so A, B, C, and D, they're all actually moving at different speeds. So even though you would think that it's constant or uniform, this inside part A, this secondary part B, this third part C, and this fourth part D, they're all actually moving at a different speed. Likewise, the center would have a different speed. So at the center, you would not actually be moving at all. You would only be spinning around. So if you're standing at the center, you're only turning. So you have zero speed because you have zero distance over whatever time. So here you're not moving, and the further out you go, the faster and faster you'll be spinning. Again, if you think about it, when you're at A, it's a short enough path to go from here to here. When you're at B, it's a longer path. So if you take a longer path at the same time, you're going to have to be moving faster. Similarly, C travels a longer path still. So if you travel a longer path in the same time, you're going to have to be moving at a faster speed. So the further out you go, the more your speed increases. At the center, it's zero, and at the outside, it will be much larger. So due to this fact, because we can't have a regular speed, even along the same object, we can't have a constant speed, we need something to be more consistent. So if we want to compare two things, we can't compare their speed, because again, we could be comparing an outside speed to an inside speed, so we need something that's a bit more consistent. And this measurement we have is called angular velocity. So it's the speed at which the angle changes. So as you start rotating around, you're going at a bigger and bigger angle. We have 180 degrees as pi radians. If you do a full circle, a full 360 degrees, that is 2 pi radians. So whichever thing would do that quicker, whichever will go the 2 pi radians, that would be the angular velocity, the speed that the angle is changing, and that would tell us more evenly if something was traveling quicker or slower. So due to this fact, we need a more consistent measurement, and this measurement is angular velocity, which is a measure of the rate at which the angle is changing. So how quickly is it going around? How quickly are you getting a bigger angle? And this is uniform for all points. So again, back up to A, B, C, and D. They all have different speeds because they're traveling different distances at the same time, but they're all move the same angle. So whatever angle this is the same angle for all of them. So when we use angular velocity, it's a more consistent measure. So again, we need our definitions and our units and everything as normal. So the definition, angular velocity, is the rate of change of angle with respect to time. So it's how quickly or how big your angle is growing over time. So again, angular velocity is the rate of change of angle with respect to time. The symbol is omega, which is given this kind of curvy W. So it looks like a W, but it's not. It's the letter omega. So here we can see this. That's your proper omega. I tend to do mine as kind of a curvy W rather than the straight line W. So if you see something like this or this, that is the symbol omega, which stands for angular velocity, the rate of change of angle with respect to time. The unit is the radian per second because it's how the angle is changing over time. So over time, s to the minus 1. So our formula is omega is equal to angle over time. So again, angle traced out over the time taken, theta over time, that's equal to omega. So on to our next topic. So this is the relationship between linear speed and angular velocity. So if you do have something moving around, how can you get the linear speed from the angular velocity? So how can you figure these out? So in the previous diagram, while A, B, C, and D from before all trace at the same angle as they move, they all have different speeds as we discussed. So we need a formula to link velocity with angular velocity. So velocity is proportional to radius. Again, on the previous diagram, the further out you are, the longer the radius, the faster you're going to be moving. So if you look at the radius from the center to A, that's a smaller radius than the center to B. So as the radius gets bigger, the speed that the thing is going to have to travel also gets bigger. The velocity is also related to the angular velocity. So if you have something spinning, the quicker it's spinning, the quicker the angle is changing, it's obviously going at a faster speed. So it's a straightforward formula, there's no squares or anything like that. So velocity, the speed that something is moving at, that is equal to the radius times the angular velocity. So this is a formula heavy section, so we have some formulas here that we're going to need to keep in our heads and use as we go forward. And we also have a lot of this extra notation. Or similar, same as always, is for radius. This is omega, which is your angular velocity, and this here is velocity. So velocity is equal to r omega. We have in the previous slide how we get angular velocity, which is theta over t. So that's our second formula here. Omega is equal to theta over t, and sometimes you will need to combine these. And similarly, in the previous one, we looked at another important formula. So when we look at this, our velocity is our distance over our time, same as always. So we'll need these different formulas, and we'll piece them together to solve a lot of problems, which we'll look at next.